Hello and welcome to Planet Critical, a podcast for a world in crisis. My name is Rachel Donald. I'm an investigative journalist and your host. Every week I interview experts who are battling to save our planet. My guests are economists, scientists, politicians, academics, and activists. They explain the complexities of the energy, economic, and ecological crises that we face today, and they reveal their solutions to mitigate the damage to our future. This is a critical time for our planet. It demands critical thinking. Go to planetcritical.com to learn more and subscribe. Today's guest is atmospheric scientist Tim Garrett. Tim studies snowflakes and clouds at the University of Utah, not just to understand climate change and the impact it's having on the natural world, but also to use these structures, these laws of physics, and these incredible formations and patterns in the natural world as a way of understanding the human world. So in today's episode, he explains how we can map economic behaviour from the formation of snowflakes. He discusses how he tracks cultural movements and human behaviour from the behaviour of snowflakes. It's a mind-boggling episode. Tim is so fundamentally passionate about what he does. I mean, I never thought I'd get that excited about snowflakes, not since I was a child, but he has me absolutely sold. It was so much fun speaking to him. I know that you're all going to get so much out of this episode. Tim manages to cover both a depth and a breadth of subjects, and it truly is one of the most striking analyses of both the ecological and economic crises that we do face today. I hope you enjoy it. Remember, if you do, please share it far and wide. If you love the episode, do consider getting a paid subscription over at planetcritical.com. Thank you so much for giving me some of your day to discuss whatever it is we're going to discuss. I've got written down clouds and global economy relationship to carbon dioxide.
Yeah, well, thank you. I'm very much looking forward to this.
Okay, brilliant. Could you introduce yourself to people that might not have come across your work yet?
Well, I'm a professor of atmospheric sciences at the University of Utah. I study clouds. That's my specialty. I study the physics of clouds, how they evolve, how they affect climate, and a huge part of my research actually right now is measuring snowflakes, developing new techniques for measuring snowflakes and studying how snowflakes swirl in the air, figuring out how much they weigh. I mean, it seems like a very inconsequential sort of topic, measuring the mass of a snowflake. But it turns out that this is one of the great unknowns in atmospheric sciences, and predicting weather and climate is very sensitive to these sorts of things. So we get to do things like put measure instruments up at ski resorts and do the laborious task of skiing to the field sites.
And how was it that you came? Sorry, but just because snowflakes is, I would have never thought that would come up. Like, how was it that you came across that as a topic that needed to be studied?
Well, I mean, that big part of it, I think, was that I live in Utah. The license plates say the greatest snow on earth, and I thought a large part of what we do is faculty. We try to do outreach, communicate science to the public, and of course episodically at a specific time every year everybody gets fascinated with snowflakes. And I thought, snowflakes is a really good physics problem. It turns out to be an incredible physics problem, and studying snowflakes is important. We really, if you want to predict even where a hurricane is going to land, knowing how snowflakes behave turns out to just the tiniest adjustment to snowflakes. It affects where the prediction is of where a hurricane will land, or how are droughts going to materialize in the future as climate warms. It depends on how snowflakes form and fall. And so I just thought this was the perfect topic because it's a fundamental physics problem. We were really struggling to do this properly, measuring snowflakes, because they're ephemeral, they're delicate, they fall and it's cold. It's hard to get out there and cold and measure ephemeral, delicate things. Turned out to be a hard problem, and very few people were doing it. Public's fascinated in it. It's important. Why not? I mean, Utah, it's great. It's good. It's just, using government grants to buy me skis is not the worst thing in the world. And no, that's legitimate. But the thing is, getting into what we're going to talk about, snowflakes are actually the basis for my model and understanding, or clouds, of how human systems work. And this has been the guiding principle behind how I approach problems, which is a fundamental belief that everything is deep down the same. The universe is not complicated. It is simple. And if I can understand one thing, that is dynamic, evolves, goes through phases of growth and collapse, then I understand the principles of how other things work, including human systems. And that's an idea that's repugnant to many people, but it's one I'm finding works. And I think it does simplify how we think about things in some really quite revealing, important ways. And so I find in my research, I'm constantly going back and forth. Like sometimes I'll look at the economic system and see how it evolves and goes through its contortions and say, wow, gee, that helps me understand how clouds go through their evolutionary cycles, or snowflakes. Or I'll look at snowflakes and look at the economy. And it's all, for me, helpful to think about these problems from multifacets.
That is fascinating. When you say that clouds and snowflakes inform your understanding then of human systems, are you talking about the atmosphere, like the atmospheric systems that then inform human systems, or perhaps all systems on the planet replicate each other in some way or another?
No, it's just systems in general. So, I mean, really, what I try to get at is understanding it's the field of thermodynamics is what I try to do. Now, I don't want to get too technical in it, but basically, if we look at anything, I mean, it could be a star, a galaxy, it could be, a tiny little critter, a cell in a petri dish, or, I mean, whatever you want to look at, that thing materialized. It came from something, nothing, to be something. And then, that required growth. And then you see in that growth these patterns that are ubiquitous everywhere you look, whether whether it's a star or you and I. You see these characteristic patterns of growth that some people call them S curves. Where you see something that starts off growing very quickly at first, and then the growth sort of continues, but maybe it's not as rapid, and then it stagnates, and then there's usually collapse. And when I say that is more or less everything, it is more or less everything. I mean, we do see other things that happen as well, like you could see a curve like this, and it goes up and stagnates, and then maybe it gets another impetus and goes off again, or it could collapse and rebound and go through a wavy cycle. But the principles that underlie that growth are ones I've been trying to think of, because we do see them everywhere. We see them in human systems, but we also see them in how snowflakes behave. So, for example, in the United States, snowflake is a bit of an epithet. We talk about, people being snowflakes. And that, they're sort of fragile, delicate people who just, at the slightest criticism, they wither away. And they've got this entirely wrong. Because, I mean, snowflakes really are the capitalists of the skies. They are the 1%ers. If you look at the evolution of a snowflake's life, it started off growing, it materialized from nothing, perhaps a little cloud droplet. And then it was really effective at getting water vapor, much more effective than the cloud droplets around it. So it had a competitive advantage over the cloud droplets due to physics of water vapor, pressure over ice versus water. But it basically took all the water vapor, stole it from the water droplets, and then it grew at the expense of the water droplets. But that wasn't enough. Like, it just became this crystal up in the sky, but then it started to fall. And it discovered a new way to grow. And its new way of growing was to collide with the cloud droplets or with other snowflakes. And it became a master of basically mergers and acquisitions. And by doing this, it could grow from something that was maybe, 10 micrometers across, something, 10 times finer than a hair, to something, real decent size. And to do that, the number of collisions that it might have done might be millions. And so that snowflake that hits the ground, maybe makes great skiing, was in fact not just a 1%er, but just some tiny, tiny fraction of a 1%er. And of course it died too. It ran out of snowflakes to collide with, and it hit the ground, and its lifetime was over. I mean, everything collapses. But, that the point here is that, you can look at something like a snowflake and, really start to think about these sort of principles that go on to say, well, this isn't actually that different from, anything else we do. I mean, a company has to grow. It has to keep growing. It doesn't have a choice.
Oh, okay. But do you really think that we are bound, that concepts perhaps, that the best of man, our creations, are bound by the same laws as thermodynamics, especially if they come from, an artistic, a creative desire? Like, why would a company have to be bound by that same law? Why could a company not, in fact, find a new curve, a circular way to grow, or to just homeostasis, to find a state of homeostasis even?
So, I mean, my answer is 100% we are bound by thermodynamic laws. I mean, that there isn't really a counter argument unless you believe in perhaps some religious manner that we are somehow divorced from everything else in the universe. We are fundamentally made of matter. We process energy. That thing in our heads consumes 20 watts. If you look at, let's say, neuronal activity in a brain obeys the same mathematical phenomena as you see anywhere else in nature. You see phenomena called mathematically power laws in the frequency and power of neuronal firing. And those power laws are seen in the size distributions of cloud droplets, because all of them, whether it's neurons or cloud droplets or people in their income distributions or critters and their sizes and numbers, they are all competing for available energy and matter. And it turns out mathematically, if you have a finite amount of energy and matter to compete for, you get certain mathematical relationships that define the behaviors.
Okay, but if I may,
Yes,
surely, in fact, it is the unlimited growth of a singular entity which is divorced from nature, because it's individual entities working as a part of an ecosystem that keep the natural world in balance, for example. So it's perhaps the continuous growth of life itself through multiple forms, but the incessant need or desire for the individual to grow will only hurt the entire ecosystem. Because that snowflake example, it forms from a water droplet, it collides millions of times, it becomes what we see, a snowball or whatever, and then it hits the ground, and that's its collapse. But that's not the collapse of snow. Snow will return every single year.
Okay, so yes, you are totally right that there is the dynamics of what goes on internally. So I could come back to my brain. So my brain does neuronal firing, or your brain does neuronal firing, and it's 20 watts is this energy. So let's say we have a 100-watt light bulb, incandescent light bulb, but your brain is 20 watts, which actually, is quite a lot of energy. And your brain is very energy hungry. And you probably notice that if you get hungry, your brain doesn't think of the same way as when it's satiated or, hasn't had its coffee. So what you have is you have a system, let's say it's an ecosystem, or a brain, or a cloud, or a company that has resources. And those resources are available to that system to consume to produce a wide variety of phenomena, including growth of the internal elements, growth at the expense of perhaps other elements, and maybe that growth collapses and then the other elements can grow in its stead. But ultimately, as they are doing these processes, all of them are consuming energy and matter. And they will run out of that energy and matter because it gets degraded to a lower level of usefulness. I mean, we use words in physics like potential energy that gets consumed. Some people prefer to use entropy. I don't like entropy. It makes lots of people confused. But anyway, there's something that's available to be used and then it gets consumed. Now, once it's consumed, absent a replenishment from somewhere else, then you're kind of done. The system is done. And so for you and I, we can keep thinking and keep thinking and keep thinking and have these beautiful, abstract, wonderful thoughts. But eventually, if we don't eat, our thoughts become increasingly primitive. And we have to eat. We have to replenish from outside. And so, so it is with ecosystems, right? I mean, if you take an ecosystem, yes, of course, the energy is coming from some other source, like sunlight. Or there has to be a replenishment of matter, which may come from the soil or from cyclical rains. And so, a key thing, when I try to think about these problems, I do try to think about systems as being, and the thermodynamic word is that they are open systems. They are not closed systems, but they are open systems. And what that means is that the system is just, it's that thing we've defined. You or I, company, cloud, snowflake, an elephant, whatever it is. But that system is open thermodynamically to its surroundings. So it does what it does in its elephantine way, or whatever it is. But that the essence of that thing can only be sustained by virtue of a throughput, and it has to be a throughput of energy and matter, resources that are available to that system that come in the form of, effectively a food, which has the energy and matter to keep that system going. And then at the same time, the system has to give off waste energy and matter. Otherwise, it will overheat. And it's no longer the same system. So you brought up the word homeostasis. I think that's precisely the right word, which there is a homeostasis. But the homeostasis does not mean that the thing is isolated. Rather, the homeostasis is sustained precisely because the system is open and there's this constant throughput. Now, there's a twist on this. And this is the one that is not so well understood. And it's a bit complicated. I've spent a lot of time thinking about this, thinking about snowflakes, how snowflakes work, and then applying it to human systems, which is that when we talk about a homeostasis, well, yes, it is sort of a homeostasis. Like you think about civilization, we have our daily activities. And from day to day, things do look more or less the same. Except they aren't. Because if you look long term, it is quite clear that civilizations grow and collapse. So we have to do a separation of timescales. One is that we have the daily timescale. Timescale is a very physics word, but we have these daily periodicities that keep us going. This is the homeostasis. But that does not forbid us from accumulating energy and matter with time and growing. And what that requires is that we consume ever so slightly more every day than we give off in terms of waste energy and matter. That there is some sort of net, mathematical word, convergence of energy and matter within the system that allows us to grow slowly over time. So to give you an idea that these timescales are very different. So I really think, I've been thinking about this lately. What is a characteristic timescale that divides humanity? And I think it's a day. We are kind of pegged to this clock of a day. But if you look at how fast we're growing as a civilization, it turns out that the timescale for a doubling of our size is about, currently, is insanely fast.
Yeah.
We will double. We'll put on as much as we have in all of the prior civilization in the next about 30 years. Which is extraordinarily fast. But still, 30 years is not one day. Mm-hmm. I mean, and then, you and I as adults, of course, we have this daily cycle. We like to think that we consume as many calories as we burn. But the reality is that all of us, it's a tiny, tiny fraction of a percent. I forget what it is. I calculated it, but it was just a minuscule fraction of a percent every day. But that percent accumulates, and then over our adult lifetimes, most of us put on about 10 kilograms.
Okay.
And then of course we die. But it's not that the growth can continue for forever. We do it all. So, could I do this for a snowflake? Once I sit down the mathematics and physics equations, I can do this for a snowflake. But I can also do it for civilization. And this was the work I've been doing, was trying to show that these concepts are actually expressible in terms of humanity as a whole. And that it enables, actually, it becomes remarkably possible to make predictions of how humanity evolves. So I've done things like develop these equations, set up conditions, looked at the 1950s. 1950s was a remarkable period. We discovered these, it's like we just came across a buffet, came across an American buffet, having lived in perhaps, Saharan Africa. And then it was incredible. And that was like something, if we're a physicist or a mathematician, when you have these sort of delta functions, delta function being something that is an instant thing that you arrive at, then you get this mathematical response to the discovery of, let's say, Saudi Arabian oil.
Right.
And so I could start at 1960 based on this energy supply, and found that it was possible to predict to a tremendously high degree of accuracy, based on modeling civilization like a snowflake, the GDP growth rate, the energy consumption, and the carbon dioxide emissions in 2010 with virtual perfect accuracy.
No.
Yeah.
Hang on. Using the exact same models from a snowflake?
Snowflake,
or
yes.
The exact same ones.
I mean, I rewrote them in a way that would be, it was my own way of writing them. No, but it's basically, it's the same model for a snowflake or a cloud droplet or whatever. And so the point here is that civilization as a whole is an open thermodynamic system. I just, of course, we think of ourselves as being beautifully complicated things, but I can just draw a circle around it, turn it into a point, say there's energy supplies, see how the circle evolves. How does it evolve? And then, and that was the thing, was that it turned out to, it was an economic, long-term economic growth model, and it works. And the form of the evolution of civilization that was predicted, that we see, is a form that you see in the evolution of past civilizations. So there's some wonderful work that has been done by Jesse Azubel, who showed that, and that's Ausubel, he's looked at past civilizations and their trajectories. And, for example, the Mongol Empire was, in terms of land coverage, that was the largest in history, but you have other big ones, of course, like the Roman Empire and countless empires throughout history. And they all go through this characteristic shape, this S-curve that I mentioned, where they go through this, and maybe they have another, peak that goes along with them. But they go through this characteristic shape that, as I mentioned, you see everywhere. We're not special.
Mm.
And I know we like to think of special, and people have some quite rude things to say to me when I try to discuss these ideas. I mean, I honestly, I don't really care that much. I just think this is a fun physics problem, and of course it's rather depressing at the end of it for what it implies, but you know, it does hit home, perhaps, you know, to think that we can be described in terms of physics equations, because we I don't know, we like to think we're different.
I think anything that can present the problem in a way that enables more people to understand better what we're dealing with, then is fantastic. And I think coming face to face very much with mankind's mortality and the mortality of the things that we create, I find it astonishing, given the fact that every other empire has fallen. We think this one won't.
Of course not. No.
Like, this one will be the anomaly.
This is different. Well, hey, yeah, and I think you bring up a really important point there, and you know, I'm being a bit too much of a jerk, you know, sort of describing these things and being, you know, sometimes unpointed about it, especially when I see a certain level of arrogance, as I perceive it in other fields, unscientific arrogance. I think it's the lack of scientific being self-critical that I find objectionable as much as statements itself. But let's say we take this work and, you know, maybe we accept it for, you know, whatever its merits may or may not be. I think you hit on 2 points that are totally key here. One is that, you know, we do want to understand how things are behaving, because if we have any prayer of getting ourselves out of these tremendous crises we are facing now, you know, in terms of resource depletion and environmental destruction and the carbon dioxide, that's up there effectively forever. We need to understand how the system works. We can't pretend you know, that it works according to some fairy tale and then hope to actually solve them. I mean, we really need to approach these problems with an open mind.
Mm-hmm.
But then ultimately too, well, I mean, let's say this is purely a deterministic physics problem, and we're just along for the ride, like a cork on a wave that's about to hit the shore. I mean, a lot of this stuff's pretty depressing, and I for myself at least, there's a question of acceptance. You know, how do we understand where we are? And does having an understanding of how we behave in a larger system, as a larger thermodynamics problem, help us psychologically with dealing with these issues? I mean, this stuff weighs on me every day, all the time. And I think thinking about these things in terms of physics problems, perhaps, maybe it helps. Everyone's different.
It's like standing on top of a mountain and looking out at the world and realizing how small you are.
Oh, yeah, sure. Yeah.
So tell me then, what are the implications of your work? Where are we on that S-curve? How close are we to the shore?
Well, okay, so that's an excellent question. So there's S-curves and S-curves and S-curves. I mean, the S-curve is for whatever you want to define. And so there's S-curves on top of S-curves.
Mm-hmm.
I'm sorry, it sounds terribly abstract, but so let's say if we were to, how are we going to define the human system? Now, an economist has their definition. Now, an economist would define the human system in terms of economic variables, and they would use things like, you know, financial value to define the human system. A physicist would perhaps look at the human system, and, well, at least I think the way they should look at it is in terms of thermodynamic throughputs. So what I mean by that is like the rate of consumption of
Mm.
energy and matter, like things like copper and wood. And those are probably different. And one major conclusion of my research is that something like the GDP is not tied to energy consumption, which is a lot of people have pointed out that there's a correlation between the GDP and energy consumption by
Yeah.
humanity. Sorry, the question.
No. I'm listening very, very closely because I've
Okay,
had people on the show talk about that.
yes, and indeed there is a correlation between GDP and energy consumption. But what my work has shown is that that is a red herring. I mean, it's not totally a red herring, but it is not the right comparison to make. There is a correlation between GDP and energy consumption. Perhaps a better one to look at would be between GDP and material consumption. That is a more close relationship. But more specifically, the better relationship is between the GDP and the rate of change of energy consumption, which is something that is not discussed, but comes out of my work as a robust empirical result. This is actually the foundation of my work, which is that the GDP can be related through a constant, a number that does not change with time, to the annual rate of change of energy consumption. Now, there are fluctuations up and down on yearly time scales. So this doesn't work so well unless you look on, you have to do a little bit of smoothing to see this. But this is actually kind of an alarming result, because what it means is that we will not have a GDP, much less GDP growth. The GDP is a manifestation of our ability to grow thermodynamically.
Yes.
So when I say grow thermodynamically, what I mean is that it is only by increasing our size, increasing our demands for energy, that we can sustain an economy.
Oh, that is a big difference.
That is a big difference, isn't it? So let's say you just have homeostasis. Homeostasis is defined by no net production. Now, let's say you just maintain a constant weight. Yes, you put on a weight in a day, but then you consume it. You are not actually doing net production. You are still consuming energy, but you're not doing any net production. Now, if you do put on weight, your energy demands increase with time. I mean, if you're a bigger person, you have to eat more. And so it is that production, what we would call the gross domestic production, that is linked to our increase with time of our energy consumption demands. And this is something that can actually be shown. Now, I have a paper out in review. The editor is one of your past interviewees, James Dyke.
Oh, fantastic.
So hopefully accepts it, but I trust his judgment. But I showed that this relationship holds, not just a correlation, but that from year to year to year, this relationship holds for the past 50 years. Right. Now, the past 50 years is a pretty long time. Lots happened in the past 50 years. Now, we don't have data before that. Sorry, you just cut out there. We don't have data before that we can, really trust. And even past 40 years is probably the best. But nonetheless, this relationship is hold. Now, this is pretty solid stuff to hang your hat on. Now, coming back to your question about S-curves. So, with S-curves, I said there's S-curves on S-curves. So let's suppose that there's an economic collapse.
Hang on. Sorry, yeah. I think I have a question before we get back onto S-curves.
All right.
Right. Sorry. And it might be a silly question, but surely if GDP is correlated to the rate of change of energy consumption, which means that we cannot sustain an economy without growing our energy consumption, can that be changed by defining what an economy is? Because if we look at, for example, I write a lot about indigenous cultures over in Malaysia, who are their economy is actually the ecosystem, and their population does not grow massively exponentially, because their environment, people come and go, but their environment is large enough that they can cycle through the different resources that they need to consume either throughout 1 year or throughout a larger time scale. So they're sustaining their economy is not a product of endless growth.
Yeah. So you bring up a great question. So part of what got me thinking about these questions was I spent 2 years as a math, science, and physics teacher on a rather remote island in the South Pacific.
Oh, cool.
And I was a Peace Corps volunteer, if you know what that is, and on this island in the Kingdom of Tonga, an outer island, the mantra was that the area was called Hapai, that Hapai is good because food is free.
Okay.
And the fact is that not all food was free. Canned mackerel from Peru wasn't free. Cookies from New Zealand wasn't free. Mud and flats from New Zealand were free. But all the local food you could not, in fact, buy. There were markets. They did. I mean, there was little stores for the luxury goods, like the canned mackerel, which was disgusting. But the local food was not something that was actually available. And you think to yourself, well, how could this be the case? Why would it be that food is free? And I think that brings to your point. I mean, I don't know if you would call Tonga an indigenous culture or not. The fairly developed nation, in fact. But there were some interesting aspects. The islands are small. They are finite. You cannot grow land. Food cannot be accumulated. It's a tropical environment. Food's rotted in a couple of days. Everybody had land through the Constitution and through family kinship relationships. So, food was free. There was no GDP for food. There was production, continual consumption, but no monetary value that could be assigned to food. I mean, in fact, for me, it's very frustrating because not being part of the kinship, I actually could not get local food. I ate canned mackerel for 2 years, and and spaghetti. It was a pretty miserable diet. So I think that gets to your point, which is that growth is intrinsic to what we consider to be a financial system. And that's thermodynamic growth, the ability to store and consume more in the future. Like you store fat and get hungrier in the future. So, S-curves. We could have collapse of the financial system, but still consume energy and matter and resources. So as we go through the phase of collapse of civilization, which will happen, I would predict that the financial system will collapse before civilization collapse. And it's going to be a longer trajectory, but we could see, let's say, the banking system disappear and things like currency become less of a consideration for more and more things, and that we gradually shift away from a monetary system to one that's more of a purely thermodynamic system. We have these pegs for growth that we call currency, that if we're not growing, what's the point?
Well, I mean, would it be good if the financial services collapsed? Short term, awful. But if we could decouple energy consumption from GDP and the economic framework that drives this kind of culture, would that mitigate some of the damage of collapse over the long term?
Well, I guess it depends what you call damages. Because the collapse fundamentally is thermodynamic collapse.
Right.
And with a thermodynamic collapse, one of the stages is a financial system collapse. but it is also a collapse of everything else, our ability to sustain ourselves. So it is, it would be still collectively a shrinking, starvation. And you can imagine what that entails.
Yeah.
Because, I mean, we see this, around the world in countries that are struggling, that are going through the phases of collapse, and there are predictable things that follow. Not fun to think about.
But important and necessary.
Yeah. And I think, one of the key objections I have to the fields of economics is that these thermodynamic considerations are not fundamental to the description of their reality.
Yeah.
But they are fundamental, very much so, to our lives, everything we do. And it's not just about money. It's about other things. And you could imagine that we might shift to, forms of government for a while that do redistribution of, whatever's out there. With the collapse of capitalism, what happens? I mean, we've seen things in history where human systems do survive. That is not under the capitalist system.
Is that what's likely to happen based on your modeling and your frameworks? What timescale are we talking here, and what are the likely outcomes?
So, one criticism that's often levied, this sort of slightly doomeristic viewpoint, is that predictions of collapse often tend to be wrong.
Okay.
And I think that's
interesting.
It's somewhat of a fair criticism, but part of it is that actually collapse is very hard to predict. It is not easy to predict when the system will fall apart. However, we are starting to understand a few things that are signs of when things may collapse. And those are when there is a period of stagnation in the system. So when the system is no longer growing, however you define the system, remember, it could be the financial system or defining things thermodynamically or however you want. When things stop growing, then that means that the conditions that previously enabled the system to grow, do net growth, are no longer there. At that point, then, well, you could stay there for a while. But at some point, perhaps at an unpredictable point, there's going to be a knock with a hammer. Maybe there's going to be lots of knocks with a hammer. And those knocks, maybe you can recover from each time. Maybe the knocks are getting bigger, maybe you're getting weaker with time, which is why you stagnated in the first place. And at some point, tap, 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 and the system collapses. That turns out to be hard to predict. However, stagnation is a clue that things will start to fall apart. Now, you asked for the time scale. I think, first guess, the time scale for when things will collapse is similar to the time scale for the growth. So right now, I said previously, we are doubling in about 30 years. We are also stagnating now in our growth rate. Our growth rate is no longer accelerating. If anything, thermodynamically speaking, our energy consumption is no longer growing the way it did before. So we are doing a stagnation now.
Okay.
So, sorry, does that make sense?
Yeah. Is this the same as like peak oil in 2018?
Yeah. So the peak oil is an example of where they got the predictions quite wrong.
Oh, okay.
Well, at least in terms of the implications of peak oil, because they were predicting a collapse that did not, in fact, happen. And it didn't happen because, well, A, it's hard to predict new discoveries. there's always these sort of the unknowns that are out there. We could discover new reserves of oil. At the same time, we're depleting known reserves. Now, if we have known reserves, let's say like the Aguar oil field of Saudi Arabia, then yes, we can start to do modeling for its depletion, and we can actually predict the peak pretty easily. But then that oil is enabling us to grow.
Yeah.
And then we might grow, and by virtue of that growth, discover new reserves.
Yeah.
Or, as we have done, access reserves that were previously unpalatable, like the tar sands. You know, that now we can process them efficiently, and they can become useful. Not sweet crude, but we can use them. Or we can develop new technologies like renewables that enable us to keep going. So, I mean, this is all part of the stuff that I try to model, which makes the problem difficult. So let's say we look at that snowflake. Back to the snowflake. That snowflake, when it grows initially, it grows by collecting water vapor that condenses onto it. And that grows it for a while, and it reaches its S-curve, and it peaks and it saturates. But then, it's got a new technique. It discovered because it got big enough. Now it's big enough, it can fall. And because it can fall, it can discover once again other snowflakes and other cloud droplets that freeze on it. And then it can, its actually its growth becomes explosive because it's got this new technique for growing. And that's the sort of thing that can be hard to predict without looking at the system many, many times over. But of course, we're on our current trajectory. We don't have the facility to consider things many times over because this is the first time really for us. But still, I would say that the stagnation now is a clue. Our energy consumption rate is growing faster than it ever has before. But that energy consumption rate itself, its rate of growth, is no longer increasing as it has before.
Right.
So that is a stagnation of sorts that suggests that it could precipitously decline. And at that point, I think the financial system's going to be in a tough shape.
But if we can have S curves upon F curves upon S curves, and if the human system is not capitalism, because that is just one system in the human system, and it's a very Anglo-centric system as well, then is it also possible that while one part of that system or one system within many is collapsing, others are being developed? Does it have to be, like it's 2021. We are, we have physicists like you that are able to model and develop frameworks and things. We have lots of technology. It's not like in, thousands of years ago when an empire was built on on a piece of land and then it collapsed because of the irrigation systems that they'd set up, and then they diverted all their water away accidentally, and bang, in, a couple of years it was over. Surely there is a way, in fact, to direct our research and our resources into recovering the systems that are possible of then continuing, growing or sustaining humankind and all other kinds on this planet.
Well, I don't think so. I think that ultimately that we're just on this trajectory, and we will consume, and then eventually that the environment gets so badly damaged that we can no longer grow, whatever the resources are. And then that tap, 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 tap of the hammer will get ever stronger. And we won't have the resilience to defend ourselves from it. And eventually that tap will get big enough that the recovery, it just turns into a spiral of decline. But I am open and hopeful that I am totally, utterly wrong.
Well,
we should ask those questions that you're asking. Why are we not asking those questions? Or why are we not asking them within this sort of physical framework where we cannot beat physical laws? And that, that's really my hope here, is that precisely what you're doing is what more people do, but currently very, very few people do. Ask, how does the system work? And if we understand how the system works according to basic physical principles that we cannot escape, can we then devise alternatives, given, like you say, how clever humanity has proven itself to be, or stupid? But, can it get around can it figure out some alternative pathway? And what would that look like? Probably it doesn't involve capitalism, but then how do we get away from capitalism to something that still sustains us?
The question I always come back to, sort of the universal question, is whatever solution, we seem to find is, but how do we do it on a globalized scale? It seems to me that because we are so small, we're just on top of that mountain. We're just a, tiny little functioning part of a larger ecosystem. This kind of godlike urge to take control, to produce, to create, and to take upon the planet's well-being as if it's something that we can manufacture rather than something that would quite naturally occur if we weren't so insistent on manipulating all of the different systems that exist. It seems to me that that's going to be the most difficult solution to find. How do we do it on a globalized scale? Are we capable of thinking, being, acting, creating on a globalized scale?
If I look at other systems, a key ingredient that you see is this element of competition. If one consumes less, another consumes more.
Well, yeah, okay. I'm going to quote people that I've had on the podcast. It was Ugo Bardi who first said this on the show a few weeks ago.
Yeah, I've met him.
He said that, there's a whole other theory of both evolution, biological evolution, and of human history, which is collaboration, not competition. We're here not because we competed with each other, but because we collaborated with one another and pooled our resources and pooled our knowledge.
Okay. And so you get these different phenomena. And again, I could come back to my snowflakes.
Please do.
And because these are just snowflakes, of course. I'm just using snowflakes just as an example, but again, I like snowflakes. I think they're pretty, but we do see two different phenomena, and it's very interesting to look at these two different phenomena because the mathematical result that you get for the distributions turns out to be fundamentally different depending on whether you have, say, collaboration, I like that word, I hadn't thought about it before, versus competition. So in the snowflake's phase of its life cycle, it's initially in a phase of competition. As I mentioned, it's competing for water vapor. It's competing for water vapor being the molecules that let it grow is called condensation. And that is something where if it grows, the snowflake grows, then the other water droplets in the cloud are shrinking. It's competition. Okay. Snowflake wins, something else loses. But what makes for great skiing is, however, a process of collaboration. And the process of collaboration being that the snowflakes get together, they collide with one another, and they become big, fluffy snowflakes. Now, here is a key distinction. Collaboration, and you just got me thinking about this, so I may be totally wrong, but collaboration is the process that shows up during the phase of rapid growth. Competition is a process that shows up when the things are more energetically constrained. So when there is only a finite amount of resources, you get competition. Collaboration happens when the resource constraint is not there. And so you pose an excellent question. And all I'm going to say is that when we are thinking about collaboration versus competition, these are two separate processes, and I could create a physical analog in the sky, but perhaps elsewhere, that suggests that perhaps collaboration, which sounds great, is actually the process that only shows up when we have increasing resource availability. And increasing resource availability may not be what we want, because when we have more resources, we actually pollute more too.
Okay, well, hang on a tick. Let's go back to the 50s. The boom time. when they were discovering seemingly unlimited access to cheap, efficient fuel. Neoliberal capitalism had been developed by Hayek before that, but that was when it really took roots. So arguably, it was at the moment of perceived unlimited resource that competition seeded itself in Western human civilization as opposed to collaboration.
Okay, well, did it?
Did it?
I mean, I don't know. I mean, I'm not a social scientist or historian or an economist, but I mean, I could easily think about the 50s and think, oh, no, actually, this was a period of massive collaboration where you had countries forming, things like NATO, whatever, or that there were trade agreements, and that there were trade networks that were created. There are big companies that evolved. I mean, I don't know what all those things are if they are not collaboration.
It's almost as if capitalism and economic frameworks that have been projected onto the world don't actually reflect human society adequately.
Oh, yeah. But I will say with this thermodynamic result that we're seeing now, which is that the energy consumption growth rate is stagnating. And that's different, very, very different than the 1950s, when the energy consumption growth rate was lower, but it was increasing like gangbusters. It was incredibly different back in the 50s and 60s versus what it is today. So now we have a growth rate that is available to humanity as a whole. We all want growth for the financial system. But there's a fixed number available for the world, which means that there is now competition for growth. If one country grows faster, that necessarily will mean that another country must grow more slowly. And you can think that that is an environment where countries might approach collaboration differently. We can't all gain because we can't grow into a faster growth rate. We are just constrained, perhaps geologically constrained, by diminishing reserves of fossil fuels.
This is so interesting to look at it from this thermodynamic perspective and the laws of physics, because it's kind of contrary to a lot of, I want to say, the narrative of like climate activists, for example, that we, or even scientists, okay, like that we need to consume less. But thermodynamically, once your rate of growth, and which ergo would be consumption as well, right? Once that starts to stagnate, then you're looking towards collapse. So these kind of signals that we're looking for to show that we're going in a better direction and we're going to be able to take care of everybody sustainably actually also point to the human system collapsing.
Yeah, and the whole concept of sustainability is kind of a thermodynamic impossibility.
Okay.
I mean, there's two things that go on. One is that we are open systems. So if we think of you sustain a constant weight. Well, you can only sustain a constant weight by consuming resources from your environment in the form of food and also heat and warmth and all these things, and exhaling matter largely in the form of carbon dioxide. Right? So that's your sustainability. But there's another thing too, which is that it works out that even maintaining a constant size is a fiction. Things are either growing or decaying. They don't maintain a constant size, and that's again because they are an open system. At the same time as they exist and interact with the environment itself, that the resources that are there are also changing size. And they can change size in two ways. One is that we deplete those reserves, but the other is that by virtue of our growth, we can discover new reserves. And so there's this balance that goes back and forth. We have depletion and discovery, and which way it tips is something that's hard to predict. But what it means is that ultimately we respond to this evolution of our resources by either shrinking or decaying ourselves. If resources are growing, we will grow. If resources are shrinking, we will shrink. But there is no stasis, because the system, coupled system of resources, the system and the environment beyond it, is itself, it's all evolving.
Would one helpful way of looking at this problem then go back to what you were discussing at the beginning, which is recognizing that the sustainability of life is not the facilitation of mankind to sustain its lifestyle, but rather the enabling of the natural systems to work together in whatever way they need to, like, and allow kind of growth and decay to occur without trying to meddle too much? It's not a very scientific question, but sorry,
No,
I only
no,
have a philosophy degree.
No, I think that's exactly the right question. I mean, again, what does this look like? Now, I could give an example here, and again, a physical example, but let's say we look at a wave on the ocean. It does this periodicity, and it, maintains a life cycle, and it does this periodicity, and it keeps on going. Now, eventually, of course, that wave will peter out due to frictional forces, or may build up due to the winds. But for a while, you have this sort of nice periodicity that goes on, and, there's up and downs. Can we achieve a sort of steady state like that? I don't think so. I don't think that's actually physically possible. But I'll just come back and say, we should be asking these questions. These are the questions that I think at least some of us should be looking at. And we just forget about these crazy economics models that are not even tested on any data. I don't even know what they come from. But, I mean, get over yourself and accept that we are actually thermodynamic systems. And then actually, maybe we could make some progress. And, but you do have to make the leap to thinking a bit like, cloud scientist. Sorry, that was very self-centered. But I mean, I do think clouds are actually uniquely special in this way because they do evolve and decay right in front of our eyes. Yeah. And there are phenomena there that are actually very well suited for representing ourselves. I mean, clouds go through phases of discovery and depletion. Some of them are really big, some of them are little tiny wispy things, and there's a whole spectrum out there. And indeed, if you look at cloud size distributions, like the sizes of the clouds versus their numbers, that mathematically they look the same as income distributions, say, for people. And I don't think that's an accident. We have resources, clouds are resources. We go through phases of S-curves of growth, then collapse. Hugo Barty calls it a Seneca cliff. And yeah, so I think we can do this, and we have models, and then we can start testing hypotheses. Like it's who cares what some economics professor at Yale thinks? It's not his expert opinion that determines whether or not something's a good idea or not. No. What matters is coming up with an actual hypothesis that can be tested. And they're, pretty well-developed tools in physics.
I am quite amazed with all of my guests, yourself included, at how widely read each of my guests are, in that, not just in their own field, but in other fields. I'm really, really, really amazed because academia always seems to essentially burrow itself into a niche. And yet here you all are kind of reading each other's works and tapping into mapping over frameworks and systems that you see elsewhere to inform your research. This is a totally out of left field question, but What do you think would be helpful to see coming from like the arts faculties that are very much sort of left out of this dialogue at them, or not entering this dialogue right now?
So I think historians have an immense role to play here. You know, history, well, what's the line? Was it Mark Twain, is it? I don't know if it's apocryphal or not, but, you know, history doesn't repeat itself, but it rhymes.
Amazing.
You know, we have analogs. Civilizations have grown and collapsed. And I think this is important. I mean, there's other things too in the social sciences. People are looking statistically at phenomena. And that's the sort of thing that you can approach with things from physics too, like statistical mechanics that describe the statistical distributions of stuff. Actually, one of the most wonderful things, I wonder if like atmospheric scientists, like James Dyke's an atmospheric scientist who interviewed him, and, you know, like whether we're sort of predisposed to thinking about these systems interacting. Like in physics, you know, actually physics itself tends, as you say, tends to narrow down and create a highly controlled system. In the atmospheric sciences, we don't, well, there's no control system. Everything is interacting in these incredible ways with so many different phenomena. And so you end up being predisposed, I think, to trying to understand things when there is nothing to control.
That's interesting.
And there was actually atmospheric scientist, actually the grandfather of modern numerical weather prediction. And back in the 1926, he started creating these models for weather prediction, Lewis Fry Richardson. But he was a pacifist. And he also came up with these wonderful numerical descriptions of wars. What were the number distributions? He's like, what was the name of this paper? On deadly corals or something like that. And he wanted to understand how wars behaved. And what he found out was that he would look at things like Manchurian bandits and gangs in Chicago. And in fact, the whole spectrum of wars from like the early 1800s through the mid 1900s when he was looking at it, and looking at the frequency of wars and their deadliness. And found that they obeyed a very simple power law relationship, a mathematical relationship that I would see in the distributions of, say, clouds. So you think, you know, wars are these complicated human behaviors, but then if you look at them, it is about competition for resources, and you see the same mathematical behavior that you would see anywhere else you see competition for resources. I think, you know, Lewis Fry Richardson was sort of a physicist, but he was doing social sciences, and I think that should be encouraged.
That's fantastic. That is incredible.
Yeah, I mean, I look it up because he really, you know, he was really one of these people who, I mean, every forecast you have for the weather is based on his work in the 20s. And they were hopeless forecasts at first. But that was the foundation. We are based on his work. And he also did incredible work in fluid mechanics, all about the place, but also social sciences. That's the sort of thing that is not encouraged currently. For me to get funding for this work I described to you, it is virtually impossible. I've got smatterings here and there, but it is virtually impossible for physicists like me to get work to study social systems.
Which is absurd.
Which is absurd.
Yeah.
But it is particularly absurd when we face these crises that we are facing.
Right.
Tribalism has no place where we're looking out for really kind of the fate of humanity. We're really struggling here. And this tribalism, I don't understand it. What purpose does it serve? Now, we need people like James Dyke, for example, who is doing this incredible thing, actually reaching out to the public. And I can only imagine it's very, very hard work, that he gets probably a lot of pushback. And it's undeserved because he is doing an important job.
Absolutely. You know, I emailed him over COP26 and I said, James, with all this talk of net zero over in Glasgow, have any journalists contacted you to discuss, the problems of net zero and why it might actually be a bit of a logical fallacy or whatever? And he said, yeah, no, I mean, a little bit, but not very much. And I said, well, I'm going to try and sort of get you out there. Like, can I send a few emails on your behalf? And people weren't interested. And I was like, how? I mean, not only is the research amazing, James is a fantastic communicator of complicated ideas.
Yeah,
I mean, he
tremendous.
really is the symbol of like what a modern academic at this time sort of needs to be. And people don't want to hear it. Tim, I'm conscious of the time that I'm taking up of yours today. This has been wonderful. I mean, I wrote down clouds and, global economy relationship to CO2, and I was not expecting this. What a wonderful interview. Thank you so much.
Well, thank you. It's fun to talk about. It's actually a good preparation to me because I have to give a seminar to my department about this sort of stuff tomorrow. So mostly just trashing economists, but it'll be fun.
I think you're a really engaging speaker. Really,
thank you.
It's a joy to listen to you, and you're so passionate.
Oh, you're an excellent interviewer. Thank you very much, Rachel.
Thank you. Tell me, who would you like to platform?
I tried to set up a group of people who were looking at these sorts of topics. One guy, since I mentioned a historian, there is a guy who's an expert on the rise and fall of Rome.
Okay.
And he is actually quite influential in these sorts of topics. His name is Joseph Tainter. He's at Utah State University. But I think all the people you have interviewed would know his name.
I actually recognize his name, and I don't know why. I don't think I've read anything, but I recognize it.
Yeah, so he might be one person to contact.
Tim, thank you so much.
Okay, well, thanks very much, Rachel.
If you want to learn more about Tim's work, I've put links to his research over on planetcritical.com, where you can also subscribe to support this podcast. Remember, if you liked this episode, please leave a review and share it far and wide. If you loved it, you can support the podcast by choosing a paid subscription at planetcritical.com. Thank you so much for listening. See you all next week.